When NASA analysts updated their tracking charts this week, one name immediately stood out: 3I/Atlas. That name belongs to an interstellar object, a visitor not bound to our sun, now cutting through the solar system on a one-way journey that will never repeat. Only 2 such objects have ever been confirmed before, and this one will soon be gone forever. But as the data sharpened, something subtle appeared. The path of 3I/Atlas no longer matched its earlier predictions. There was no collision, no nearby planet close enough to pull it off course. NASA confirmed that the object had shifted slightly under the influence of a non-gravitational force, a finding consistent with official tracking updates released by NASA's Near-Earth Object Program and partner observatories. The change was small, almost invisible to the public, yet serious enough for scientists to pause, recheck their models, and flag the anomaly. In the near vacuum of space, motion is usually predictable. So when an interstellar object alters its course without impact or gravity, it forces a deeper question. What natural process could quietly push a wanderer from another star system while it passes through our cosmic neighborhood today? On July 1, 2025, an automated telescope system quietly recorded a faint point of light moving against the background stars. At first, it looked ordinary, the kind of detection that observatories log every night. But as the Atlas survey refined the object's motion, its true nature became clear. This was not an asteroid born with our sun. It was officially designated 3I/Atlas, also known as C/2025N1, and its path told a remarkable story. The object was traveling on a steep hyperbolic trajectory, meaning it was moving too fast and at the wrong angle to be gravitationally bound to the solar system. In simple terms, it was passing through, not settling in, and once it left, it would never return. That single fact immediately placed 3I/Atlas into an extremely rare category. Before it, humanity had confirmed only 2 interstellar visitors, 1I, Oumuamua in 2017 and 2I Borisov in 2019. Each discovery reshaped how scientists think about the space between stars, and 3I/Atlas arrived with the same weight of expectation. Unlike planets or comets that circle the sun again and again, this object offered a one-time opportunity. Every hour of observation mattered, because there would be no second chance to study it on another pass. Its speed through the inner solar system, measured in tens of miles per second, gave researchers only a narrow window to gather data before it faded back into interstellar darkness. As telescopes around the world turned toward it, scientists focused on answering basic questions. How fast was it moving? What was it made of? How did it behave as it approached the sun? These details were not academic curiosities. Interstellar objects are physical samples from other star systems, carrying information about how planets form beyond our own cosmic neighborhood. That is why attention quickly spread beyond astronomy circles. Space agencies, research institutions, and observatories coordinated tracking efforts, knowing that even small measurements could have lasting value. The brightness of 3I/Atlas increased as it moved inward, allowing more precise observations of its surrounding cloud and developing tail. Nothing about its appearance suggested danger to Earth, and NASA made it clear that its closest approach remained safely distant. Still, the object's importance had nothing to do with risk. It was about access. For the first time since Borisov, scientists were watching material from another star system respond to our sun in real time. And hidden within those familiar-looking datasets, numbers updated night after night, the first signs of a subtle deviation quietly began to emerge. As tracking continued night after night, scientists began comparing the predicted path of 3I/Atlas with where it actually appeared in the sky. At first, the differences were almost invisible, the kind of variation that can hide inside margins of error. But as more data came in, the pattern held. The object was not exactly where the models said it should be. The discrepancy was small, but it was consistent. Each updated position placed 3I/Atlas just slightly off its expected course. In celestial mechanics, consistency matters more than size. Random noise fades. Real effects repeat. And this one repeated clearly enough that researchers could not ignore it. Naturally, the first explanations were the simplest ones. Scientists checked for signs of a collision with another object. None were found. There were no sudden jumps in brightness, no debris cloud, and no abrupt change in motion that would suggest an impact. The data showed a smooth, gradual deviation, not the violent signature of a crash. Next came gravity. Could a planet have tugged 3I/Atlas off course as it passed through the solar system? Once again, the numbers did not line up. The object never approached any major planet closely enough for gravity alone to explain the shift. Its trajectory stayed far from the regions where a hidden gravitational encounter could plausibly occur. That left researchers with a narrower set of possibilities. In space, motion follows strict rules. If an object changes speed or direction without a collision and without a strong gravitational pull, the cause must come from the object itself. Something had to be pushing back, even gently. This idea is not as strange as it sounds. Astronomers have seen similar effects before, especially with comets. When material escapes from a comet's surface, it does more than create a glowing tail. The escaping gas produces a tiny reaction force, like a slow, uneven exhaust. Over time, that force can slightly alter the object's path. What made 3I/Atlas different was not the size of the deviation, but the context. This was an interstellar object arriving from another star system, carrying unknown materials shaped by a completely different environment. Any force acting on it was more than a technical detail, it was a clue. To confirm the effect, teams compared observations from multiple telescopes and independent tracking systems. The results converged. The deviation was real, it was measurable, and it followed a smooth curve rather than a sudden jump. This was the moment when a new term moved to the center of the discussion. Not collision, not gravity, but non-gravitational force. A subtle push, acting continuously, quietly reshaping the journey of a visitor from beyond our solar system. To understand what was happening to 3I/Atlas, scientists turned to a process they know well: outgassing. This is the same mechanism that gives comets their glowing appearance as they approach the sun, and it begins at the surface. When an icy body warms up, frozen gases trapped inside begin to escape. Carbon dioxide and water ice transition directly from solid to gas. As those molecules rush outward, they do not leave quietly. Each burst of escaping gas produces a tiny push in the opposite direction. Individually, those pushes are weak. Over time, they add up. Astronomers have observed this effect for decades. Many comets slowly drift away from their predicted paths as sunlight heats their surfaces. The process acts like a natural engine, uneven and imperfect, but real. It does not fire in a straight line. It depends on where the ice is exposed, how fast the object is rotating, and which materials are closest to the surface. In most cases, outgassing is subtle. The force is far weaker than gravity and far weaker than anything humans could feel. Yet in the vacuum of space, even a gentle, continuous push can alter a trajectory if it acts long enough. This is why comet paths must often be recalculated again and again as they move inward. When researchers applied this framework to 3I/Atlas, the numbers began to make sense. the direction and scale of the orbital deviation matched what outgassing would produce. There was no need to invent new physics or extreme explanations. A natural process was sufficient. What made this important was confirmation. Independent teams modeled the object's motion using standard cometary outgassing equations. The results aligned closely with what telescopes were seeing. The deviation was not random. It behaved exactly like a slow reaction force driven by escaping gas. NASA emphasized this point in public briefings. There was no evidence of artificial propulsion, no sign of mechanical thrust, and no indication that the object was being guided or controlled. The behavior fit well within known comet physics, yet this explanation did not close the case. It opened a new layer of questions, because while outgassing itself was familiar, the way 3I/Atlas was doing it was not entirely typical. Most comets from our own solar system remain quiet until they are much closer to the Sun. Their activity ramps up gradually as temperatures rise. 3I/Atlas, however, was already showing signs of gas-driven motion earlier than expected. The mechanism was natural. The force was weak, the math worked, but the timing felt unusual, and that detail suggested that 3I/Atlas was not just another comet. It was a comet shaped by a different star, carrying a different history, and responding to sunlight in a way that hinted at unfamiliar chemistry beneath its surface. As observations continued, one detail about 3I/Atlas became increasingly hard to ignore. The object was already showing signs of activity while it was still far from the Sun. At distances where many familiar comets remain dark and inert, 3I/Atlas was already releasing gas strongly enough to influence its motion. For astronomers, this timing stood out. Most comets from our own solar system are dominated by water ice. Water remains frozen until a comet moves relatively close to the Sun, where temperatures rise enough to trigger visible activity. Before that point, these objects are often quiet, almost indistinguishable from asteroids. 3I/Atlas did not follow that pattern. Its activity began earlier, at a stage where sunlight should have been too weak to drive significant water-based outgassing. This early response suggested that something more volatile was at work, materials capable of turning into gas at much lower temperatures. That realization shifted the focus toward chemistry. If the force altering the trajectory came from outgassing, then the composition of the surface mattered deeply. Different ices react to heat in different ways. Carbon dioxide and carbon monoxide, for example, can sublimate far from the Sun, long before water ice becomes active. This behavior pointed toward an origin beyond the familiar environment of our solar system. Objects that form in colder regions around other stars can preserve large amounts of these highly volatile compounds. When such an object enters a new star system, it begins reacting sooner, almost as if it is waking up earlier than expected. For 3I/Atlas, this explanation fits both the timing and the magnitude of the observed force. The early onset of activity explained why the deviation appeared when it did. The object was not defying physics, it was obeying a different set of thermal conditions shaped by a colder birthplace. To test this idea, scientists turned to spectroscopy. By analyzing the light reflected and emitted by the cloud surrounding 3I/Atlas, researchers could identify chemical signatures hidden within the glow. These measurements act like fingerprints, revealing what materials are present without ever touching the object itself. The results were telling. Spectral data showed strong signs of carbon dioxide, consistent with what astronomers observed earlier with 2I Borisov, the second confirmed interstellar object. This similarity reinforced the idea that interstellar comets may share common traits, distinct from many comets native to our solar system. With chemistry now aligning with motion, the picture became clearer. The early activity of 3I/Atlas was not a mystery caused by unknown forces. It was the natural outcome of volatile rich material encountering sunlight for the first time. And with that confirmation, attention shifted from whether the object was behaving strangely to what its behavior could reveal about the environments where other planetary systems are born. As 3I/Atlas moved closer to the Sun, its behavior became easier to observe in detail. The increase in brightness was steady and pronounced, allowing telescopes to resolve features that had been faint or hidden before. What emerged was a clear picture of an active comet, not an ambiguous object. Spectral analysis revealed that carbon dioxide played a dominant role in the outgassing process. This placed 3I/Atlas firmly in line with what scientists had previously seen in 2I Borisov. Both objects showed chemistry consistent with formation in cold, distant regions around other stars, rather than within the warmer environment of our own solar system. As sunlight intensified, a distinct coma formed around the nucleus. This cloud of gas and dust expanded outward, surrounding the object in a visible halo. Within that glow, two separate structures became apparent. One was a dust tail, composed of heavier particles gently pushed away by sunlight. The other was a plasma tail, made of ionized gas shaped by the solar wind. The separation between these two tails was unmistakable. Each followed its own direction, responding to different forces, exactly as comet physics predicts. This was not a partial or unusual display. It was a complete, well-developed cometary system unfolding in real time. For scientists, this mattered deeply. The presence of both a dust tail and a plasma tail confirmed sustained, organized activity rather than a brief or accidental release of material. It showed that the nucleus was continuously supplying gas and dust as it warmed, reinforcing the outgassing explanation behind the earlier orbital deviation. Equally important was what observers did not see. There were no signs of rigid structures, no unnatural reflections, and no patterns that would suggest solid, metallic components. Every feature matched what natural processes produce when volatile rich material is exposed to solar radiation. NASA and partner observatories emphasized this point as images and data were released. The object's appearance remained consistent with established comet models even as its interstellar origin made it scientifically valuable. By this stage, the question was no longer whether 3I/Atlas was active. That had been clearly demonstrated. The real concern was how it would handle the most extreme part of its journey. Because the Sun was still ahead, and the true test for any comet, especially one arriving from another star system, would come at perihelion, where heat and stress reach their peak. October 29, 2025 marked the most critical moment in the journey of 3I/Atlas. On that day, the object reached perihelion, its closest point to the Sun. For comet scientists, this phase is always watched with caution. It is where many newly discovered comets fail. As a comet approaches perihelion, solar heat increases dramatically. Ices sublimate faster, internal pressure builds, and weak structures can fracture or collapse. History offers many examples of comets that brightened briefly, only to disintegrate when they came too close. For an interstellar object like 3I/Atlas formed around a different star under unknown conditions, the uncertainty was even greater. Observatories around the world focused their attention on this narrow window. They tracked changes in brightness, monitored the shape of the coma, and looked for sudden drops in activity that could signal breakup. A sharp decline, an asymmetric cloud, or a spreading debris field would have indicated that the nucleus had failed, but that moment never came. As 3I/Atlas passed through perihelion, it remained intact. The coma persisted, the tail stayed coherent, and the object continued along its path without any signs of catastrophic disruption. The outgassing continued in a controlled, gradual way rather than erupting violently. This stability was significant. It showed that the nucleus was not a fragile shell barely holding together. Instead, it suggested a solid internal structure capable of withstanding intense thermal stress. Whatever materials made up 3I/Atlas, they were arranged in a way that allowed the object to survive its closest encounter with the Sun. NASA confirmed that post-perihelion observations matched pre-perihelion models. There was no sudden loss of mass, no unexpected change in rotation, and no drastic alteration in its overall behavior. The same physical processes that had been observed earlier simply carried on. For researchers, this was an important checkpoint. It reinforced the idea that 3I/Atlas was a natural cometary body, not a fragile anomaly. It also meant that the earlier orbital deviation could be explained without invoking extreme scenarios. The object had arrived from another star system, endured the harshest part of its passage, and emerged structurally sound. That resilience added one more piece to the picture. 3I/Atlas was unusual because of where it came from, not because it broke the rules of physics. Its survival at perihelion showed a natural but durable construction shaped far beyond our solar system. As scientists reviewed the growing archive of data on 3I/Atlas, comparisons with earlier interstellar visitors became unavoidable. The most obvious reference point was Oumuamua, the first confirmed object of its kind, discovered in 2017. That object entered the solar system unexpectedly and left just as quickly, giving researchers only a brief and frustrating glimpse. It showed no clear coma, no obvious dust tail, and no classic signs of cometary activity, yet its trajectory shifted in a way that could not be explained by gravity alone. That contradiction turned Oumuamua into one of the most debated objects in modern astronomy. Because of those missing features, scientists were forced to rely on indirect clues. Theories multiplied, ranging from exotic ice compositions to extreme shapes, and in some corners, even artificial origins. The lack of visible outgassing made every explanation feel incomplete. Oumuamua became famous not because of what it showed, but because of what it did not. 3I/Atlas told a very different story from the start. From early observations onward, it behaved in ways astronomers immediately recognized. Gas release was visible. A coma formed naturally around the nucleus. As it approached the Sun, its brightness increased in a smooth, predictable way. Dust and plasma tails separated clearly, responding to sunlight and the solar wind exactly as comet physics describes. This clarity changed everything. Instead of guessing at hidden processes, scientists could watch them unfold directly. The same non-gravitational force that puzzled researchers in Oumuamua now had a visible cause. Outgassing was not inferred, it was observed. The direction and strength of the force matched the release of gas seen in images and spectra. Just as important was consistency. Multiple observatories, using different instruments and methods, reported the same behaviors. The data aligned across optical imaging, spectroscopy, and orbital tracking. There were no contradictions between what the object looked like and how it moved. Each dataset reinforced the others. Equally revealing was what scientists did not find. There were no unusual reflective flashes suggesting metallic surfaces. There were no rigid shapes resisting erosion. There was no evidence of controlled thrust or directional changes inconsistent with natural processes. The nucleus behaved like a body shaped by chemistry and heat, not engineering. NASA addressed this contrast openly. Improved detection systems, faster follow-up, and coordinated global observations meant that 3I/Atlas was studied far more thoroughly than Oumuamua ever could be. As a result, many of the uncertainties that fueled earlier speculation simply did not apply here. By this stage, the conversation had shifted. The question was no longer whether 3I/Atlas was artificial or dangerous. Those possibilities had been steadily ruled out by consistent evidence. Instead, scientists began focusing on a more meaningful perspective. The true value of 3I/Atlas was not in mystery, but in clarity. It was a natural object from another star system, observed in detail as it reacted to our Sun. Not a cosmic riddle, but a rare sample, a messenger of chemistry, formation, and history from beyond our solar system. And that made 3I/Atlas far more important than speculation ever could. As 3I/Atlas continues its journey away from the Sun, the picture surrounding it is now clear. This interstellar visitor does not carry danger, and it does not represent anything artificial or engineered. NASA has emphasized that its trajectory poses no threat to Earth, and every major observation supports that conclusion. The slight shift in its course was not a warning sign, but a reminder of how even natural forces can quietly shape motion in space. What 3I/Atlas truly brings is something far more valuable than fear or mystery. It carries material formed around another star. Its gases, dust, and internal structure preserve conditions from a region of the galaxy we cannot otherwise reach. For scientists, this makes it a rare physical sample of another planetary system, observed not in theory, but in real time as it responds to our Sun. The behavior of 3I/Atlas also delivers a broader message. Our solar system is not sealed off or isolated. It exists within a dynamic galactic environment where material is constantly exchanged. Interstellar objects pass through more often than we once believed. We simply lack the tools to notice them. Now, with modern surveys and faster detection systems, these visitors are finally coming into view. Each new object reshapes how scientists model planet formation, chemistry, and the evolution of star systems. The fact that 3I/Atlas behaves like a natural comet, yet formed elsewhere, suggests that the processes shaping worlds may be more universal than we imagined. Different stars, different environments, familiar physics. And that raises a quiet but powerful question. If objects like 3I/Atlas are not rare, how many others have already passed by unseen? How many are moving through our cosmic neighborhood right now, leaving subtle signatures we are only beginning to detect? That is the real significance of this discovery. Not alarm, but awareness. We are learning to notice what was always there. Share your thoughts in the comments and subscribe to mindgap to keep exploring the hidden stories moving through space, often closer than we realize.